Good afternoon and welcome to MAE 113, Calculus for the Liberal Arts. My name is Richard Carr and this is Lecture 29, the Logistics Curve. And this is April 1st. And hopefully you can hear, hopefully the audio is coming through clear. Again, just give me a thumbs up in the chat. Excellent. So, first thing I should announce is that because of the holiday that's coming up, starting tomorrow and going through till Monday, I think that won't give you enough time to work on an assignment or something like that. So, I said I was going to post the assignment on Tuesday. I didn't. So what I'm going to do is I'm going to post the assignment today. And then the quiz will be next Thursday. Excellent. Okay, so that means I better just pull up the calendar. And that'll be the 8th. 8th of April at the beginning of the lecture. So is that okay? Like, does that, I know it's kind of falls out of our regular routine of usually having it on a Tuesday, but just a show of in the chat, that's okay, or we can have it Tuesday. Okay, sounds good. Excellent. And I should also have a look at how many people are just watching. Okay, there's only 8 people watching. So, okay. Well, it's a small class then for those that are watching. So, previously, kind of like recapping from our previous episode. So previously, what we had seen was we had a differential equation where we had it proportional to itself. So the rate of change was proportional to itself, and the k was some constant. And we knew, or what we had found, is that previously, or that the solution to this, if we solved for y, that it was a exponential form. So it was some sort of like c naught times the exponential function, the growth rate k times t. And I can also kind of rewrite this as 1 over y dy by dt is equal to k. Now, this was used to model growth that is proportional to the current amount. But the issue with this kind of a model is that the growth is unbounded. So this is unbounded growth. And we had talked about that, for instance, like bacteria kind of growing continuously, exponentially. It, will eventually hit, the edge of the petri dish. Like it runs out of room to grow, and then like the rate starts to slow down. So we want to start to consider something where we have the growth bounded. So if the growth is bounded, or what I mean is the amount. And same thing here. So this is unbounded amount. Because the growth is it's constant in this case. It's proportional to the original amount. So for instance, if I consider an environment, so we consider an environment like a field or some sort of settlement. So we have an environment. It can only support a limited number of people. So we'll say that it can only support a 0 number of people. And so what we'll say is that as the population P starts to approach that limit of that, well, the A0, the number of people, the growth rate starts to slow down. So the growth rate actually decreases to 0. So what I'm trying to say is that the amount of a population is kind of reaching it is reaching a horizontal asymptote. So that's what I'm trying to say. So for instance, if I draw like a little picture to go along with that, the behavior that we want to model is something like, I'll draw in a horizontal asymptote. So y equals a0, so that's my kind of bound. Then I kind of expect it to look something like that. So you can see that the population is growing, and then as it's getting to a0, it starts to slow down. So one way of describing that, or one differential equation to do this, is if I work similarly like this, I'll start with not using y. I'm going to use p, and right here is going to be my population. So it'd be something like y equals p. So again, p is population. I'll be working with time. So what I'm going to do is I'm going to start out like this up top here. So I'll start out with 1 over p, and then dp, so the change in the population over time, so the rate of change, is equal to k. And the way that I'm going to bound it, or to kind of slow it down proportionally, is to do 1 minus p over a0. So what this would say is that this will start to cause this to slow down. As p increases, it'll get this number will get bigger, which means that 1 minus a 1 will, so this starts to approach 0 as p goes to a0. So as p goes to a0, 1 minus p over a0 goes to 1, which means then that as that goes, the whole thing, oops, and I'm running off the page, sorry. Which means then that as p goes to a0, that this whole thing here, k of 1 minus p, goes to 0 as p goes to a0. So it works out for us. So now the real question is What is P? So we have it in this differential equation. We have to solve for that. So let me just have a check. Okay. So I have this differential equation. Oh, I imagine the formula. Let's see. I imagine the formula would also model the alcohol content during the fermentation of beer that many of us will be drinking tomorrow. Yes, there's a limiting factor to a lot of things. What I plan to do, or what I plan to show, is we're going to use this to model an epidemic, that if we're going to work within a certain population of a small town, that we'll model this as that it's some sort of jointly proportional to the number of people that are infected compared to the number of people that aren't. So we can actually model fairly simply with a very simple model, kind of showing the, assuming that like an epidemic has this kind of a behavior, that the spread will start to slow down as it reaches 100%. So again, I have my original differential equation. So the idea is to reduce it down to something that we already know how to solve. So that's a problem-solving technique that we use a lot in math and just in general. So we're going to reduce it to a problem we already know. So the idea is that we're going to do a change of variable. And instead of using P, I'm going to kind of rewrite P as a form of what I'm going to call Q. So we're going to do a change of variable. And we're going to show that this, rewritten as this change of variable, is equivalent to 1 over Q dP over dQ. Not Dairy Queen, but the derivative of Q with respect to time is equal to K. There we go. And the nice thing about that is that that equation has the form, so 1 over Q dQ by dt is equal to K, which is in the same form as this. So if I can show this, that means it's the same as this kind of form, and then I have an equation it's going to look like that. So that's what we're going to do. We're going to try to reduce this problem back to a problem that we've already resolved. So that's the plan. And so I'm going to show that, which means that I'm going to prove it, which means I'm going to start out on the left-hand side and work my way to the right. So I'm going to show that 1 over Q dQ by dt is equal to K. So take a deep breath, and we'll start with the left-hand side. Okay. So what this says is that I have 1 over Q, and I'm going to take the derivative of Q. And I know what Q is. I'm setting it to P over A naught minus P. And now I have to differentiate this. So I have to use my quotient rule. So I'll use my quotient rule, which is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. So the derivative of the top is just dp by dt times the bottom minus, I'm going to leave the top alone, so p times the derivative of the bottom. So that's, I'm going to just write d, like just say I'm going to have to take that derivative with respect to t. So a naught minus p all over the bottom squared. And I'll leave this dp by, oh, maybe I'll just pull out that, this. So I'm going to pull out that, so I'm left with this, what's left in the numerator. So dp by dt times a naught minus p minus, so I have p, and then I take the derivative of this. A naught is a constant, so I don't have to worry about that. And I have to take the derivative of p with respect to t. So that becomes dp by dt. And I have a negative and a negative, so again, I have to remember, respect the negatives. So the negative in the negative becomes positive. Okay. The next thing that I can do is I can factor out this dp by dt. So when I do that, I have a naught minus p plus p, which means that these p and minus p can cancel. And so I'm left with 1 over this q a naught minus p squared times a naught dp by dt. So what I'm going to do is just kind of pair this together. So I know that q is equal to, because I had changed my variable to p over a naught minus p. So p over a naught minus p. And that if I did 1 over q, that would be a naught minus p over p. So I have 1 over q, so that is equal to a naught minus p over p. 1 over a naught minus p squared. I still have the a naught dp by dt. And so this one can cancel, and I can get rid of that squared there because I'm multiplying everything, so that's okay, I can cancel it. So everyone's just, hopefully, I know the algebra can kind of look a little daunting, but what I'm going to do is I'll kind of just rearrange here. So I'll do the 1 over p here, dp by dt. So again, I'm just moving this here. I'm taking this p, I'm putting it here. And then I'll take this a naught and move that over there. So what have I got so far? After doing that manipulation, I know what that is equal to. Because I've done my change variable, but I already know what it is. So this 1 over p dp by dt is equal to this. So I can just copy that down. So that is equal to k times 1 minus p over a naught. And then I still have a naught minus p and what else can I do? I'll leave this alone, so I'll have the a naught over a naught minus p. I have the k. And what I'm going to do is I'm going to rewrite this 1. So instead of 1 here, it's going to be a naught over a naught. So when I do that, I can rewrite that as a naught over a naught minus p, which means that I can do this. I can cancel this here and this here. I can cancel this a naught out. And after doing all that cancellation, I'm just left with k. So what I've shown there is therefore that 1 over q dq by dt is equal to k. So that's good. Which means that from this, I know that my q is equal to c naught e to the kt. And now all we have to do is substitute our values, or change the variable q back to p. So that was kind of the trick. And so we found this, which was q is equal to c naught e to the kt. So we change back to p. Right, and our q is equal to p over a naught minus p. So the way that we can do that is we have to solve for p for this one. So I can rewrite this. I can have q a naught minus p, sorry. Okay, and I have q a naught minus qp equals p, and I'm just, solving for it. So I brought this over to the right-hand side. It's changed signs. And now I can factor out the p, so I'm left with 1 plus q. And I'm just going to finish that off so that I have q a naught is equal to, and I bring that over, so that's 1 plus q. And what I can keep doing is I'm going to simplify it just a little bit more. So I'm going to divide everything top and bottom by q. So I'm going to do q a naught over q, and 1 plus q over q. So that means that I'm left with a naught over, so here's the q here, q over q, it gives me 1 plus 1 over q, or q to the minus 1. I already know what Q is, so it's right up there. C naught e to the kt minus 1. So I can apply that negative in there, e to the minus kt. And that's it. So I know it was a couple of a page to show that, but what we proved, or what we showed, that idea of relating the rate of infection or the population, like this model, we showed that it was equal to a naught over, and I have c naught to the minus 1, but I'll just call that b naught. So 1 plus b naught e to the minus kt. So there's the formula. So this is what we call the logistic curve. And this is where a naught and b naught are constants. And let me draw a picture to go with that. So you kind of know what I drew it previously, but let's just annotate that a little bit more. So the first thing to know is that the y-intercept, that's when p is 0. So in that case, I have a naught over 1 plus b naught e to the minus k times 0. And we know that e to the 0, so we can't bring the negative exponents up because of the addition. That's right. Yeah, in terms of this up here. No. So what I have to do is, to simplify it, I have to apply my algebraic manipulation to everything. So yes, I divided out that q, and that's it. Exactly. And I can apply this negative 1, though, because of my law of exponents. So again, very similar to that, I have a and b to the n. It's okay, I can do a to the n times b to the n. So in this case, I've done to the minus 1. So I have a b to the minus 1, a to the minus 1 times b to the minus 1. The thing that you cannot do, and I saw this lots of times, and it's not just this class, but every time we teach calculus, we always see this a plus b, whoops, to the n. And we spent so much time doing expansion, right? Foiling, and that, again, this is not, that's not true. I see a lot of that. So like, remember, it was a squared plus 2ab plus b squared. Yep, okay. It's good that you tell me that it's, so I'll stop talking. But I do see stuff like this where, you know, if we can't really handle something like that, where it's a plus b. Again, I saw lots of people do this. And that's not, you can't do that. So, okay, so just getting back to that, I have e to the 0, which means that this is 1. And so my y-intercept should be 1. So a naught plus 1 plus b naught. So this one should be a naught over 1 plus b naught. And my horizontal asymptote should be the limit as t goes to infinity. I'm so used to writing x. So t going to, and I have a naught over 1 plus b naught e to the minus kt. So again, as this t gets really, really big, this value gets really, well, if I can't remember, I might as well pull out a calculator and I can show you. So as t gets really big, say something like e to the minus 2, e to the minus 3. So as it gets really big, this number gets really, really small. So that is also approaching 0. So it means that this approaches 0, which means that this whole thing here goes to 0, which means that I have 0 times b naught. So that also is going to be 0. So in the limit, in the denominator here, I would have 1 plus 0. So then I'm just left with a naught. So up top here, I'll draw in a little dotted line for my horizontal asymptote. I have my y equals a naught. So again, my curve will look something like, we'll go through the y-intercept and do something like that. And so that curve here is a naught over 1 plus b naught e to the minus kt. So other things to point out then, so like if you're going to make a model or something like that, you can figure out what your bound is, like what it's going to be getting really close to, and you also have to have like an initial estimate of where you're starting at. And the other thing that you'll need to figure out too is a k. But let's do an example of that. Handling an epidemic. So this is kind of our example that we'll do. Sorry. And I'll make sure I number the pages. Here's 3 and 4. So it says one model to explain the possible behavior of how an epidemic spreads is that the rate of spread is jointly proportional to the fraction that is infected, so the fraction of the population that is infected, and the fraction that is not infected. So we'll start out with a rural town of 5,000 people. At the beginning of the week, there's 160 people that have the disease, and at the end of the week, 1,200 people have it. They ask us to find the formula, so we're going to basically find that, what we've already done. Find the formula relating the fraction to the number of weeks since the disease was first noticed. So we'll start out And I'll just kind of define my variables. So I'll say that f is the fraction. A town with the disease. And they also tell us that t is the number of weeks. So they told us that how it's related, and they said, you know, it's going to follow that logistic differential equation that we had. So 1 over f. Oh, so maybe I'll just bring back that sheet. So this is the logistic differential equation. So it's 1 over p dp by dt is equal to k times 1 minus p over a naught. So I'll just copy that. But instead of using p, I'm going to use f, because that's the variable that we're going to use for fraction. So df. After saying that I'm going to use f, I wrote p. 1 minus f over a naught. Now, the nice thing about this is that this is what the curve is going to look like. And since it's a fraction, I know that my upper bound has to be 1. So my a naught is 1 because it's a fraction. I'm using like a decimal or whatever. So I know that this is equal to 1 because, you know, cannot have more than 100% infected. Okay. Which means then that I can rewrite that. I'm just going to write df by dt is equal to f times k 1 minus f. There we go. And because we've already solved this, I can rewrite that. So I know what my a naught is. It's 1. So it's 1 over 1 plus. I don't know what the b naught is yet. And I don't know what the k is yet. So that's what we need to figure out. So we need to find b naught and k. Okay. So what we were told is that initially at t equals 0, the fraction, so we were told at the beginning here that 160 people had the disease out of 5,000. So we're told initially 160 out of 5,000 had it. So that's equal to 160 over 5,000. Or 16 over 50 should have given you 32%. right? So if you had doubled it, boom, boom, just like that. What else can we do? We also know that this is equal to 1 over 1 plus b naught e. And then I have kt, but the t is 0, so here is 0. So I have 1 over 1 plus b naught is equal to 0.032. And just solving for b naught. And using our calculator, I got 30.25. So from that, therefore, my equation for this town is 1 over 1 plus 30.25 e to the minus kt. Oh yes, and I still haven't found that k yet. So I need to use that second piece of information. So this was the first part here, and then I have the second part, which is at the end of the week, we have 1,200 people have it. So that means, oops. So grab another piece. We're told that t equals 1, that at f of 1, it's 1,200 over 5,000, or 12 out of 50, doubled out, which should be 0.024, or 0.24. And I still just have to solve that again. 0.24 equals 1 over 1 plus 30.25 e to the minus k times 1. And then we solve for k. So to do that, I have 1 plus 30.25 e to the minus k is equal to 1 over 0.24 I'll bring the minus 1 over here and then divide by 30.25. So I have 1 over 0.24 minus 1 divided by 30. Oh. Divided by 30.25. So that is approximately 0.1047. And then I need to take the inverse of this. And lastly, we have ln e to the k. The k comes down in front. And k, oops, and I should have a ln here as well because I'm applying it to both sides, ln So K is equal to ln of 9.553, and that is approximately 2.26. So now that we've built our model, let me just put this over here. Our model then is f of t is equal to 1 over 1 plus 30.25 e to the minus 2.26 of t. So now that we have that, we can answer the remaining questions. So for that one, for B, it says, show that in 11 days over half of the town is infected. So B, we have 11 days. This example is being tricky because our t here is measured in weeks. So we need to convert that to, our time is equal to 11 over 7. So there's 11 days and there's 7 days in a week. So 11 over 7. So it doesn't work out to be a nice number. So I will leave it as a fraction. Oh, just a second. So we just substitute in that value. So we have f of 11 over 7 is equal to 1 over 1 plus 30.25 e to the minus 2.26 of 11 sevenths. And that works out to approximately 0.54. So that means that, over 50% is infected by day 11. And the final one is asking us, how long does it take for 4,000 people in the town to be infected? So that means about 80% of the population. So, C. They want us to solve for t in this case. So we'll start out with the fraction, which is 80% of 1 over 1 plus 3. So 1 plus 30.25 e to the minus 2.26 t. And we solve for t in this case. So I'll flip this. So I get 1 over 1/8 is equal to 1 plus 30.25 e to the minus 2.26 t. I'll have 1 minus, 1 over 0.8 minus 1 divided by 30.25 e to the minus 2.26 t, which means then that e to the 2.26 t, I'm just going to flip it, 30.25 over 1 over 1.8 minus 1. We're still not finished yet. Because I have this. And then I apply the ln to both sides. So that comes down in front here. Which we know is 1. I still have this on the right hand side here. And I just have to divide by this 2.26. So t is equal to ln of all this stuff all over 2.26. And if I put that into the calculator, 30.25 divided by 0.8 minus 1 divided by 2.26, 2.122. So that means that, therefore, after approximately 2 weeks, %80 of the population is infected. Okay, thanks for hanging in there. I know it was a long question, but again, thank you for tuning in. I'll post the assignment later today, and I wish you the best of the holiday coming up. And oh, so sir, will A0 always be 1? No. A0 can be, in this case, what we're using the A0, we're using it as a fraction, but remember the A0 can be any number. So for instance, I can have something like this where have a great long weekend, or creating, yes, I know. We'll see you for office hours. Okay, yes. And I will be there for office hours as well from 1 to 3. For instance, like A0, for example, a vehicle, a vehicle can only go so fast, it can't go faster than the speed of light. So that's kind of the speed limit of our universe. So like it can get really, really, really close. Like we can't get really close to it. But for instance, like that would be, the upper bound would be like a speed limit. You could have, in terms of, instead of using F, you could have used the actual population. So instead of using like A naught to be the fraction, like we were using F for a fraction, we could actually use real numbers instead. So like, for instance, we could have used the town's population of 5,000, and then we could adjust our equation appropriately. But it's a good question. Again, you can put it to like a temperature. Piece of metal we're warming it up, and then it's approaching kind of a temperature that we want it at. We can also have it as a learning curve. So for instance, like our memory can only remember so many things, and we can get really close to it, but we start to slow down or something like that. So I hope that answers that question. Yes, so the answer is no. A naught can be, it's a constant. It can be any number. Perfect. Again, if you want to chit chat or if you have questions, feel free to drop by big blue button. I'll move the little link in our Moodle to like this week, and I'll be there to answer more questions. Again, enjoy your weekend, and I will see you all next Tuesday. Take care.